with a new chapter, chapter 5, on continuous random variables. Okay, so before we discuss specifically continuous random variables, we would like to address some general properties for arbitrary random variables, which can be discrete or continuous, or not discrete, not continuous. Okay, just general. All right, so okay, so we recall that so in the last chapter, okay, we define a real valued random variable to be a function, okay, from the sample space X, okay, to the set R of all real numbers. Subject to a certain general property right, so that is for a general random variable, just a function from the sample space X to the set of all real numbers R, subject to a certain general property. And but as mentioned, okay, in the definition of a discrete random variable, X taking on one of the possible values A sub I where I is a countable index, say, right? So in such a definition of a discrete random variable, it is required that so it's required that for any A sub I this is subset of the sample space must be an event of interest. i.e. In the sigma algebra F. A member of the sigma algebra F. So that we can assign a probability P of x equal to a sub I to this event of interest. Okay. All right, so that is particularly for discrete random variables. Okay. Now, but in practice, as well as in theory, okay, it's extremely convenient okay, and useful to describe, to be able to describe events of interest to be studied, all right, by a random variable x or a collection of random variables in the form. Okay, x is in I, x omega I where I is an interval of the real line. I.e. Interval can be, they are basically 4 types of intervals, as you have learned from calculus. Okay, so A can be equal to minus infinity, because if when A is equal to minus infinity, B is equal to positive infinity, then this interval is the whole real line. Okay, or it can be half open, half closed. Okay, in this case, A and B, but B cannot be equal to infinity because we put the closed, so we include the right end point. Or half closed, half open. Or closed interval. Okay, so we particularly interested in event which can be described as this way. Okay. In here, I'm sorry, I used the same symbol because in here I is the index, say, but here I is interval because the both of the word begin with I. Yeah, but please distinguish the meaning of the same I in different contexts. Okay. All right. So we have 4 different types of I'm sorry, of intervals. All right. All right. So that a probability can be assigned to this event of interest. Okay, so in mathematics, we developed a theory. You usually ask for a theory which will be convenient or useful to solve practical problems as well as theoretical problems. Okay, so in many situations, it's subject to our choice. So here, we like to develop a theory such that if we can call a function x from the sum space to the set of a real number to be a random variable, we would like that by using this so-called random variable, we can describe event of interest. So we ask that this subset of x should be in the sigma algebra F. In that case, then we can assign probability, all right, to such an event because this event becomes to be an event of interest. Okay, so the precise definition of a random variable x, it's a real valued function x on the sample space. Okay, such that x in I, okay, it's in the sigma algebra F for any interval I of the real line. Okay, so that is the precise definition. So this sentence gives the so-called certain general property for a random variable to satisfy. Any questions? And now, so we recall the definition. Oh, by the way, before I do that, okay. the definition of a discrete random variable in the last chapter coincide with the above definition of a general random variable. Okay. Please check it. Okay. Okay. Now we recall the definition of the cumulative distribution function abbreviated as CDF f of x of a random variable x. Okay, so that f of x is defined to be the probability of x less than or equal to little x. Okay, and this is saying that x is in okay. All right, when we write x less than or equal to little x, it means that x is in this interval. Okay, so these two description means the same. These two mean the same event. Okay. Okay. All right, and so we know this is an interval, right? And so and from this requirement of random variables, this is an event of interest. So we have a probability measure on this event of interest. Okay, so CDF is well defined. Okay, and in the last section of chapter 4, there are some important properties of the CDF. Okay, and I would like to review those properties here. But before that, I want to the continuity of probability function. All right. And the continuity property of the probability function is developed in the last section of chapter 2. All right, so I would like to revisit this property. Okay, so let E1, E2, En be an increasing sequence of events in the sigma algebra F. Okay, so suppose we have an increasing sequence of events. So the events becomes bigger and bigger. Okay, and we define the limit of this increasing sequence of events as, okay, so we define, so the limit to be the union of En. Okay? All right, and we will use En go up to the union of that union to denote this case. All right, so when we have an increasing sequence of events. How about a decreasing sequence of events? So on the other hand, the limit, so we will define the limit of a decreasing sequence of events E1 include content E2, content etc., content En, content everything. In F is defined as the limit of En and goes infinity to be the intersection of this En. Okay. And we will use En go down to the intersection of En to denote this case. Okay, so there are two cases that we can define limit of a sequence of events. When the sequence of events is an increasing sequence of events or a decreasing sequence of events. Okay, so for these two situations, we can define limits of events. Okay. All right, so this is just definition. And so proposition 2.6.1 in chapter 2, we call the continuity of probability measure. All right, so if En is a sequence of it's either an increasing or a decreasing sequence of events in the sigma algebra, then if we take the limit of the probabilities. Now, the reason why we may have the limit is because that if we have an increasing sequence of events, by proposition 2.4.2, we know the probability of E1 would be less than or equal to probability of E2, less than or equal to, less than or equal to probability of En. So their probabilities becomes to an increasing sequence of non-negative numbers. Okay, so it's going up. Okay, so it's going up. Right. And for monotone sequence, we may ask for the limit of this sequence of non-negative numbers. Okay. And as we know, probability always bounded by 1. Okay, bounded by 1. So we have a monotone increasing sequence with upper bound. Now, by the completeness axiom of real numbers, the completeness property that if a increasing sequence has an upper bound, then this sequence will have a least upper bound. And this least upper bound should be the limit of this monotone increasing sequence. Okay? So that is the property. It's the so-called the completeness axiom. It cannot be proved. Just like Euclidean geometry, that we have some axioms for real numbers. Okay, and one of them is called completeness. Okay. Okay. So this limit exists. We know from calculus. And what is this limit? The limit, the proposition says that this limit is equal to the union of En. And that is the limit of En by our definition. Or okay. This is for increasing sequence. This is for decreasing sequence. Okay. For decreasing sequence, we also know probability would be equal to probability of E2 okay, and so this is the monotone decreasing sequence, the probability of En, and it has a lower bound. The lower bound is 0. Again, by the completeness axiom of real numbers, it has this greatest lower bound, and this greatest lower bound will be the limit of the sequence. Okay. All right, and this proposition says that this limit is the probability of the limit of this sequence of event. Okay. Okay. So formally, we can say that the limiting function and the probability function, all right, can exchange the order. Okay. Okay, so formally you can see that. And the proof is that we consider an increasing sequence first. Okay, so that it's become bigger, right? So this is E1, E2, E3, okay. And now we define different set. Okay, so we let F1 to be E1, and we let this part is F2, it's E2 minus E1. Okay, and then this part F3 is E3 minus E2. Okay, so define Fn to be En minus 1 for all greater than E1, where E0 is defined to be the empty set. Okay, because the sequence is starting from 1, right? E1, E2, E3, etc. Okay, so this is that. Okay, and it can be seen that En is the disjoint union of I from 1 to n of the Fi. Right? Because, for example, E2 is the disjoint union of F1 and F2. And E3 is the disjoint union of F1, F2, and F3. Is that all right? Okay? And so we have disjoint union like this one. And also, the union of En, you can see, becomes the disjoint union of I from 1 to of Fi, right? So that the union of En, because this union may not be disjoint. Of course, not disjoint, because what? Because that E1 is contained in E2, E2 is contained in E3. So, okay. So now, with this definition, the union of En becomes the disjoint union of Fi. Okay? So we have these two. Now we can apply countable additivity of probability measure, right? So the reason why we want to express En as a disjoint union of Fi, or this union as a disjoint union of Fi, is because that we want to apply countable additivity of probability measure. Okay. So by the countable additivity of P, so we have probability of En becomes probability of I from 1 to n Fi. This is the joint union. So this becomes 2I from 1 to n probability of Fi. Okay? And the union of En becomes to the disjoint union of Fi and I from 1 to infinity of P of Fi. Right? So these two, of course, you may say the first one is from finite additivity. That's fine. But because finite additivity is derived from countable additivity, right? In chapter 2, we derived that. So you may say, okay, everything go to the countable additivity of probability measure. Okay. But if you want to distinguish the reasons for each of them, then you can say that. Okay. Anyway, so we have that. Now, but this is the serious sum. Okay, this is the serious sum. Okay, and there's a serious sum. It's by definition okay. It's a limit of the partial sum, right? From the definition of a serious sum, because it's converged. From here, we know this is from the countable additivity of probability measure, right? So it's converged. So this is 1, and what is that? This one here is probability of En. Okay, and so this is the probability of, by definition. Okay, so we establish the identity here. Okay, so we establish if the sequence is an increasing sequence of events. Okay, now consider a decreasing sequence okay. Then En complement. It's an increasing sequence. Okay. And we have just proved the proposition for increasing sequence of events. And so that limit P okay, because this is probability of limit. Okay. But this one is 1 minus P n. Okay, and this one is 1 minus P of okay. And by De Morgan's law, so the complement becomes 2 okay, and this is okay. So 1 minus the limit is equals 1 minus probability of. So that limit n in P of En, it's the probability of the intersection, and this is the probability of the limit. Okay, because En is a decreasing sequence of events, so the limit of En is just their intersection. Okay, so okay, so this is by De Morgan's law. Okay, so continuity property can be proved in the following those ways. Any questions? All right, so if no questions, now we will use continuity of probability measure to prove a few properties of CDF of a random variable. Okay. We revisit some general properties of the CDF of a random variable in section 4.10. Okay, and so proposition 5.1.8. So I summarize in this proposition. Okay. So let f of x be the CDF of a random variable x. And then we have first f of x is it's a non-decreasing function. Second, the limit of x goes to infinity, f of x is equal to 1. Third one, the limit x goes to minus infinity of fx is 0. The first one. F of x, it's right continuous. i.e., for all b in R, f b plus defined to be, so the right limit is b plus 1 over n goes to infinity is equal to f of b. Okay. So b plus 1 over n will approach to b from the right hand side of b. Okay, from the right hand side of b, right? And as n goes to infinity, this number will approach to b from the right hand side. And you can see that the limit exists because it's non-decreasing. So, and we find that this is called a right limit, right, in calculus. And the right limit will equal to the value of the CDF. So it's called right continuous. The fifth one, the left limit b minus 1 over n. So this is defined to be the left limit. The left limit exists and is equal to this probability. And this is the probability that the function, the random variable x, has value in this open interval. Okay? In this open interval. And the last one, f of x has a finite jump at each point of discontinuity. And has countably many points of discontinuity. Okay. Okay, so let's see how to prove that. In here, the reason is here that if A is less than B, then the interval will contain, okay? And this implies the probability of less than equal to the probability of because this is the bigger set. Oh, by the way, I'm sorry. No. So implies X in contained in all right. I give you a formal proof. So consider all right. So consider AB. Okay. Now omega in the event, if only if x omega is less than or equal to A. Okay. Remember, this is okay. So this event is defined here. So if omega is in this subset of sample space, then S of omega, right, by its definition, less than or equal to A. So this is implied as of less than or equal to B, okay, because B is greater than or equal to A. Okay, so right, and so this is implies that omega is in the set. Okay. So every member of this subset is a member of this subset. So we know this event is smaller than this event. And so the probability, so f of A, which is probability of x less than or equal to A, will be less than or equal to probability of x less than or equal to B, which is f of B. Okay. Right? So this is the first case. Okay. And this one is proposition 2.4.2. I think so. All right, so f of x is non-decreasing because if B is greater than or equal to A, then FB is greater than or equal to FA. Okay. So that the first one is proof. Second one, okay, so consider an arbitrary sequence increasing sequence of real numbers such that the limit of xn is equal to infinity. Okay, so it's unbounded. So suppose we have an arbitrary sequence of real numbers, and the limit is goes to infinity. Okay, so okay, and so now x is less than equal to x1 would be contained in x less than equal to x2, contained in x less than equal to x3. It's increasing sequence of events. Okay, in the sigma algebra F, right? Such that the limit of this increasing sequence event, which is it's equal to the sample space. Okay, because the x of n goes to infinity, so it's become bigger and bigger. Okay. If you want to know the reason, this is because that for any omega in x, okay, x of omega is in R, okay, because it's real value the function. Okay, so there exists an n such that okay. Why? Because xn goes to infinity. So and x of omega is the definite value, a real number. Okay, so we can always there exists and if all the xn less than equal to x omega, then this sequence is bounded, and there is the least upper bound, so the limit cannot be infinity. Okay. All right. So there is an in this. So this implies that the omega is in x less than equal to xn for some n. So this is implies the omega is in the union of, okay, right? So any element in x is in this union, so that x is a subset of the union. Okay, but the union should be a subset of x, because x is our universal set, the sum space. All right, so we have the inequality. We have equality here. Okay. So this is implies that as we expect. Okay, as we expect. All right, so we have that. We have that. Now we can apply by the continuity of probability measure. Okay, so the probability of x, so 1 is the probability of s, so it's the probability of the limit n goes to infinity of x, this is equal to this to xn, and this is the limit of n goes to infinity of probability. Okay, so this is from the continuity of probability measure we just proved. And what is that? This is f of n, f of xn here. So we see that the function value sequence goes to 1. Okay, and this is true for any sequence goes to infinity. Okay, so let's see. For any monotone increasing sequence goes to infinity, the corresponding function value of CDF, all right, approach to 1. So this is just the definition for that. For x goes to infinity, f of x, it goes to 1. So the meaning, what is the meaning of this limit? You have to go back to your calculus textbook, because this limit of function means if you take any sequence of x goes to infinity. For here we just it's appropriate to take monotone increasing sequence of x. All right, goes to infinity because infinity is above there. Okay, so for any such sequence, the corresponding sequence of function value will approach to the same limit 1. This is always true for arbitrary sequence of. So you can select different sequence of real numbers goes to infinity, right, to have this property. That means this is just this definition of this notation. Okay, so we define the limit of a function by using limit of sequence. Okay, if you still remember, this is just last year, right? Because you are a sophomore student only, right? Most of you, I know some of you may be senior or junior, but most of you are sophomore students and you still remember your calculus. Okay. So fresh, because for me, that would be more than 40 years ago. Okay. All right, so that is 2, right? How about the third one? The third one, you see, we are going to this limit. So we will consider a sequence of real number goes to minus infinity. So we will take decreasing sequence of real numbers, and the limit is minus infinity. Okay, so consider an arbitrary decreasing sequence of real numbers, x1, x2, such that the limit of xn n goes to infinity is equal to minus infinity. Okay, so there are infinitely many such decreasing sequence of real numbers goes to minus infinity. Okay, infinitely many. Okay, and so we can apply the same approach. Then x less than equal to x1 will be contain x less than equal to x2 because this is going down. Contain. All right, so this is a decreasing sequence of events in the sigma algebra. Okay, such that the limit of this sequence of event is the intersection of x less than equal to xn, and you can prove this intersection is the empty set. This is the empty set. All right, so I ask you, please show it at home. Okay, show it at home. Okay, in here I show it's equal to x, right? By this relation. But I ask you to show that this intersection is the empty set. Okay, so by the continuity of P, 0 is P of the in the empty set, right? And this is the P of limit n goes to infinity of x less than equal to xn. Okay. Okay, so this is from here. Now I apply continuity of probability measure. So this is the limit so from here, just like here, okay. Okay. So the sequence of function values goes to 0, okay, as n goes to infinity. And this is true for arbitrary decreasing sequence of real numbers goes to minus infinity. Okay, so that's limit x goes to minus infinity, f of x is equal to 0. Okay. That is the third one. Okay, so let's take a break of 5 minutes to 2:35. Okay, so we continue to prove the rest 3 points. The first one, okay, so the first one, all right, this is a decreasing sequence of real numbers. Such that limit is B X is less than equal to B plus and would be then equal to over 2 X less than equal to B plus 1 over N is a decreasing sequence. It's a decreasing sequence of events in sigma algebra. And the limit of okay, so the limit, which is the intersection okay, the intersection is equal to X equal to less than equal to B. Okay, again, please show it at home. Okay, so when you take the intersection, okay, this is equal to this one. Okay, so f of B, which is the probability of X less than equal to B. Okay, and this is probability of the limit n goes to infinity of X less than equal to B plus n over 1. Okay, from our and this is equal by the continuity of probability measure. Okay, so this is continuity of P. Okay. This one, and this is by definition is f b plus, so it's the right limit. Okay, so the right limit is equal to the right limit of f at b is equal to the function value at b. Okay, so f is right continuous. Okay, at any b. Okay. Now, in general, actually this is not good enough. You should in general you should so you should, okay, and such that Bn, so the Bn will converge to B. Okay. And the greater than B. Okay. So you should select B1, B2, B3, Bn. All so it's decreasing, but approach to B. Okay. So it's going down to B, arbitrary. And this is Bn, B1, B2, Bn. Okay, so this is Bn and Bn, and you can get the same result. Okay, so this is Bn. Okay, so the right limit, should be the limit. If the right limit exists, that means that for any decreasing sequence of real numbers goes to B, then the limiter has the same. Then the limiter exists and the same for arbitrary decreasing sequence Bn. The reason why I just use one particular decreasing sequences, so actually this is B plus 1, B plus, you can say plus, okay. I just omit B. The reason for me to use this particular sequence is because that we have proof f of x is monotone, non-decreasing. So if you look at approach to it from the right side, the function value will non-increasing. So you will have a non-increasing sequence, and the limit always exists. Okay, and so it's just a convenience, yeah. But in calculus, if you want to show the limit, because the right limit, so the right limit should be written in this way. X go down B, f of x, right? Is defined. So f of B plus means the limit for all sequence of x go down to B. And the f of x, this corresponding function value sequence will have the same limit for arbitrary xn sequence go down to B. If you go back to check your calculus textbook, okay, so what you have to prove is to select an arbitrary sequence, not just this particular sequence only. So I just the same situation is here. You have to, in general, we have to write the x go up to b and f of x. So this is defined. So the left limit, if b plus, the left limit of a function exists at b means that if you approach b from the left hand side, so go up to b, okay, and x never equal to b, but will approach to b. Then f of x, any such sequence, the function value at this sequence of real numbers x of n, well, has a limit, all right, and all these limits will be the same. Okay, so this is very strong statement. You know, if we write a notation like this one, we are considering arbitrary sequences x of n goes to b. Okay. Okay. And this particular sequence is just a convenient one, because that we know f of x is already monotone function. Okay. 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 So we show that this is right continuous, and okay. And the first one, and the fourth one, the fifth one, consider, so we consider xn go up to b. Okay. So the notation means that x1, okay, and the limit of equal to b. Okay, so we consider arbitrary sequence of that. Then so you go up. So we have contain. Sorry, this is big X. Right? It's an increasing sequence of events, so that the limit because it's going up, so it's union. Okay, and interestingly, this union is equal to x less than b, not less than equal. Okay, so let's show it. Okay, very interesting. If we take the union of those event, because this event monotone increasing, right? Become bigger and bigger and bigger. Okay, and if when you take the union, you find this union actually is equal to this event. It's x less than b. Not like here. You take the intersection, very interesting. Then you have x less than equal to b. Okay. Okay. So you have to do it by yourself. to comprehend the idea in behind. Okay, and so that the probability of x less than b, is equal to the probability of the limit and this is the limit and this is the limit so you can see that for any sequence x and go up to b, the corresponding function value sequence goes to the same limit. So by definition, so f of this is just the left limit x go up to b is equal to and so that the CDF may not be left continuous because that this may or may not so what we can have is that this is less than or equal to probability of x. So what we have is we have less than or equal to, and it is possible that we have strict inequality. All right, we may have a strict inequality. So we cannot put equality here, just only inequality here. So this is the last one. Fx has a discontinuity. It's a discontinuity at a point b if and only if f of b minus is less than of f of b. Because f of b is equal to f of b plus. By right continuity, we know that. If this is true, if this is equal, then of course f of f is continuous at b, right? So if the left limiter is equal to the right limiter and equal to the function value, then we know the function f of x is continuous at b. That is the definition of continuity. So we have a discontinuity at the point b if and only we have that. And the jump at a point of discontinuity nu et has size fb minus f of b minus, and which is so this is probability of x equal to b. So it's equal to the value of its PMF. And greater than 0. So the the jump. Okay, and now as we draw a picture of the CDF, this is 0. So we know that we may have so the depth limit exists, all right, but not equal to something like that. So we have jump. Okay, so f of x has a finite jump, and the jump, because the jump is the PMF of the random variable at b, so that the jump has finite size because the size is p of b, and it has counted many points of continuity. Why? Well, each point of discontinuity. So here we have a point of discontinuity. Okay? Now, each point of discontinuity corresponding to an interval. So here we have corresponding to an interval in the y-axis. Okay? All right, so this goes to, so this point goes to this interval. This one goes to this interval. This goes to this interval. Okay, so now from the figure, that each point of discontinuity correspond to corresponding to an interval going to an open interval or just interval. Okay, an interval which is all right, and all the corresponding intervals are disjoint. Okay, so you can see they are all disjoint because it's monotone increasing. All right, so they are disjoint. Each interval. Okay. So maybe I think I write open, I think. Open all this corresponding. And each interval contains a rational number. Okay. So every interval contains at least one rational number. Okay. Because every real number can be approached or by a sequence of rational numbers. Okay. So, right, but the set of all rational numbers are countable, so that there are countably many points of discontinuity. Okay, and then we have done the proof. Okay, now we have some correlates from the previous proposition. Okay, so for any CDF f of x, if we want to find the probability of this event, okay, this is actually open half-course interval. Okay, and it's a finite interval. And this is actually equal to FB minus F of A. Second, A it's in open interval, so that would be B minus F of A. And third one, half cross half open, so that would be A minus 1. And the fourth one, B it's F of B minus F of A minus. Okay. So by using the CDF, we can find the probability of arbitrary finite intervals. So we have 4 kinds of finite intervals here. Okay, and some of them may involve the left limit of the CDF function. So FB minus here. Okay, and the proof as an exercise. Okay. All right, so they are all general properties of the CDF of general random variables. now we now define continuous random variable. Okay. So a random variable x is called continuous. Okay, if p of x equal to a is 0 for all a in R. i.e. f of b minus equal to f of b equal to f of b plus for all b. Okay. Remember the jump. If we have discontinuity, the jump is equal to this probability mass function. So if the probability mass function is all 0, okay, so the PMF of a random variable x is an all 0 function, all 0. Then there is no discontinuity. Okay, right here. And so the left limit is equal to the function value is equal to the right limit, as we know. Okay. Which means that f of x is a continuous function. Or equivalently. If it's a continuous function. Okay, so to see a random value to be continuous, you will check its CDF. If the CDF is continuous function, then this random variable is a continuous random variable. Okay, and equivalently, its PMF function is an all 0 function. Okay, its PMF function is all 0 function. Okay, now a continuous random value may be pathologically maybe hard to deal with. So a special case is it's called absolute. So a random value is called absolutely continuous. If, all right, we call it absolutely continuous. If there exists a non-negative and integrable function f, okay, a non-negative integrable function on R, okay, such that for any interval I of the real line, the probability that the random variable has value in this interval can be expressed as an integral of this non-negative function over the interval. Okay? So if you can find a non-negative and integrable is crucial, because you need to do this non-negative function should be an integrand, so that we can evaluate this integral over arbitrary interval. This interval can be finite, so it's definite integral. If the interval is infinite interval, then you should consider indefinite integral, as you have done in calculus before. But for anyway, this integral should be able to be evaluated so that it is integral. Okay? So to see if a random variable to be absolutely continuous, you have to find such a function f satisfying this identity for all interval. Yes, please. Oh, here. Mm-hmm. This is equal to 0, right? The same as, so this, actually I give you 3 equivalent statement, right? First one, second one, and third one. So these 3 are equivalent to each other. Okay. All right. So such a function f is called a probability density function called PDF of x. Means that you may find many other probability density functions satisfying this property. Indeed, if you can find one, you can find even many others. I will show you later. Okay, so probability density function is not unique. Okay, right? But we usually take one which is typical. For example, we ask for a PDF which is continuous, or if it cannot be continuous, it has discontinuity. Okay, as less many points of this as possible. Okay, if it is continuous, this is beautiful. Okay, would be beautiful. Okay, but anyway, PDF is not unique. Okay, so there are infinitely many PDF, as you will see later. So okay, so that's that. And okay, so let me give me several more minutes to finish a sentence before we leave the classroom. Note that usually this integral, this notation is equal to AB, the definite integral, no matter the interval is open, half closed, or closed. Okay? Why? Because the differential at the point is null. Okay, so that if you include endpoint or not will affect the evaluation of the integral. Okay? So that it's from calculus. Okay, don't forget it. Also, the total probability, okay, because x is real valued, so this event is actually the total event, and so this is, so we know that this is require almost out of the bed.